Alright, in this video we'll be going over the basics of ROS with the main goal that after watching this video you will be capable of moving on to the ROS related exercises of the course. In more specifics, the contents of this lecture, first of all we're going to go through an introduction to ROS, what it is and why it's used. Secondly, we will be talking about the ROS graph, which is basically the overall architecture of a ROS solution, the different components and their connections, going over the fundamental components such as packages, nodes, topics, messages, services, and actions. Thirdly, we'll be going over ROS development, sort of what main files there are when you are implementing solutions in ROS. Then fourth, we'll be going into ROS package customization. ROS is offering very good default solutions, but here we will basically go through things that you can customize when you're making your own specific solutions. And fifth, we will be looking at ROS tools for development. So ROS, for convenience, ROS is offering quite a wide variety of tools that you can use when you are developing robotic solutions, for example, automated driving or mobile robotics. And the learning outcomes of this video, after watching this video, you should be able to, first of all, understand what ROS is and why it's used. Secondly, understand the basic architectures of ROS-based solutions. Thirdly, apply ROS in simple robotics development tasks. And fourth, have a basic knowledge of the most commonly used development tools in ROS. These are very much aligned with these topics that we will be going through. There's quite a lot of topics to tackle, so I recommend taking short breaks between each individual sections of this video. Alright, so in the first section, an introduction to ROS. Just a quick disclaimer before going further. Throughout this video I will be talking about ROS, and what I really mean is ROS 2. Since there's now two main versions of ROS. There has been ROS 1 and there is ROS 2. Traditionally, ROS has been used to just refer to ROS 1, but since ROS 1 is now outdated, with end of life being early in 2025, I'll make things simpler by just saying ROS when I refer to ROS 2. This is just a disclaimer because when you're looking online, you will find materials that are saying ROS, and that refers to ROS 1, and then ROS 2 is most commonly ROS 2. But here, to keep it simple, when I say ROS, that just means ROS 2, because we will only be talking about ROS 2. Now, what is ROS? ROS stands for Robot Operating System, but maybe a bit confusingly, it's not actually an operating system of its own. ROS is actually middleware. What middleware is, it's basically a software that exists between other blocks of software. You can think of middleware as a sort of software glue. So it basically glues together different packages of software. So if we look at the image here on the right, you can see sort of the building blocks that you would expect in a autonomous driving solution or a mobile robotics solution in general. So you have blocks such as planning, localization, navigation, and so on. And what ROS does, it basically offers you very convenient tools for connecting these different software implementations. So if you're doing robotics development, ROS offers a very convenient modular solution that connects your individual programs. ROS does this through this DDS data bus, which is something that you can very conveniently use to exchange information between your software components without having to think too much about the details of how to implement this. So you can basically focus on creating modular software solutions for different robotics tasks, and ROS is taking care of the communication between these packages. basically of being a really convenient tool for this modular development. As opposed to if you were implementing everything from scratch, you would have to implement these software packages and also then implement all the communication between them. Now, this is maybe a bit more of a development point of view. Naturally, in industrial real-time critical applications, you still have to think about that communication. But in terms of development, ROS is mainly taking care of that, and you don't have to worry about that. And now, ROS, for why we're learning ROS related to automated driving, well, it's a very commonly used tool in mobile robotics and automated driving. For example, AutoWare, which is basically the world's leading open source project for automated driving, is built on ROS. And well, as with the figure on the previous slide, how ROS functions in this AutoWare stack. Well, first of all, you again have a sort of like modular pipeline where you have, for example, sensors connected to sensing, which is then taking that raw sensor data and passing that into, for example, localization, localizing the vehicle perception, processing that sensor information into more detailed scene understanding, planning, which is basically the route planning, path planning that the vehicle needs to be doing, then detailed control, map data, and so on. Vehicle interfaces are something that are a bit more implementation specifics. But anyway, again, looking at this AutoWare stack, the architecture, you can see that it's basically software blocks implementing different functionalities. And as AutoWare is implemented in ROS, then basically these green arrows here are taken care by ROS. So that the information exchange is handled by ROS without the developers having to think too much about it. Okay, so why ROS? This is something I already explained a little bit, but to be more specific and highlight the key points. First of all, modularity. As said, you can implement individual blocks of functionalities, of software, and then ROS connects these to one another. The communication framework with this DDS is offered to you very readily. So this allows a very convenient integration of individual software components. Second point, community. So ROS has been around for a very long time. ROS 1 was released in 2007, and development continues actively. So there is a very active community of developers working with ROS, and this has naturally led into the availability of a large number of open source packages available. So when you're implementing your robot functionalities, you don't have to implement everything from scratch. There are vast libraries of open source solutions that you can implement on your robot or automated car. And again, these convenient developer tools that were mentioned in the beginning. Tools such as RVIS and RQT can be used for visualization. More on this later on. There's functionalities such as ROS bags for recording data. There's a number of tools that make development with ROS very convenient. As I've mentioned, ROS is mainly used for development, but with ROS 2, there are basically capabilities of implementing real-time functionalities, and thus in industrial deployment of ROS systems is something that there is more and more interest towards. And some have already implemented ROS solutions for safety critical use cases. A real world example of this is Apex AI. You can check out their web page. They've basically done safety certified solutions based on ROS. Now, this is not very straightforward to do. You have to understand the inner workings of ROS quite well to ensure this, but it's something that you can still do with ROS. But again, mainly it's used for development right now. Yeah. And just a quick note, it's not like the ROS would be the only robotics middleware or framework that there would be. There have been several other options over the years, but ROS is the most widely adopted with the largest community. So it can be argued that it's the one that you should be learning. All right, jumping now into ROS graph. So what is a ROS graph? ROS graph is basically network of nodes in a ROS system and their communications with one another. So it's basically the sort of architecture of your ROS-based solution. So let's jump into basic vocabulary when talking about these ROS-based solutions. And we'll use this image on the right as a kind of simple example to illustrate what we are talking about. So starting with a package is basically a single ROS-based software implementation. It contains a ROS-based software entity that can be shared with others or installed on a machine. So basically a single unit of software prepared for ROS. And in the illustration on the right, this entire building could be a single ROS package containing all the implemented functionalities. Now the second thing to consider is a node. And what node is, it's kind of the basic unit of ROS functionality. So kind of a node is typically a piece of code, a small program that implements a certain functionality. And in this figure on the right, these colored silhouettes of people, these could be the nodes. These are the nodes in this illustration. And then the third one, a topic. A topic is a data stream that the nodes communicate through with one another. So on the illustration here, topics are basically these rooms where you can see the nodes communicating with one another. And then fourth is a message. A message is basically a predefined format with which data is exchanged within topics. So again, in this illustration, we have a topic, we have nodes, and the nodes are talking with one another via messages. And when it comes to writing and reading these messages, it's called subscribing and publishing. So subscribing means that you are reading information from a topic, and publishing means that you are writing information to a topic. Yeah, okay. So with a little bit more detail, let's start with the nodes first. Node is generally the smallest computation process in a ROS solution, generally written with Python or C++. On this course, we'll be doing everything in Python, and also in this video, I will be showing examples of Python-based nodes. C++ is, of course, very commonly used with ROS, but on this course, we'll be going with Python for the convenience. But yeah, nodes are sort of the fundamental building blocks in a ROS solution, and also the enabler of modular design. So your solutions are very modular because you split your bigger software into these single functionalities, the nodes, which are then communicating with one another. And as a sort of very, very practical example, when you're executing nodes, so you have a piece of code that you want to execute in ROS, you can execute it with a command like this. So ROS2 run, and then as arguments you give the package and then the node. And so the main thing that nodes typically do is they perform processing, and then they deliver their data from that processing to other node via topics, called publishing or subscribing. In addition to this topic-based communication, nodes can also act as servers or clients for services, which are separately called procedures, and they can act as servers or clients for actions, which are discrete robotic tasks for execution. I'll be talking more about these later on in the video, but services and actions are very similar, with the main difference being that services are typically quick, are quick to execute, and actions are basically longer tasks to execute. But okay, a little bit more in the topic communication. In the previous slides, you saw the figure with the illustration of the building, but let's go a little bit more into the specifics. So as said, this topic communication is the most common format through which nodes communicate through one another. The data is communicated as messages, which are these standard data formats which are specific to a topic. So in a topic, you communicate via a predefined message type, and nodes act as publishers or subscribers. Publishing meaning that they send messages into the topic, and subscribing meaning that they receive messages from the topic. And this can look something like this. So you have multiple nodes, and multiple nodes might be connected into a single topic. They might be publishing, they might be subscribing, or they might be doing both. Yeah, let's look at this a little bit more visually, what the publishing and subscribing can look like. Here we have a node that is acting as the publisher, and it's sending a message through the topic, and the message is delivered to a node that is a subscriber. Kind of simple one-on-one communication. A little bit more advanced, so as said, there can be multiple nodes publishing or subscribing to a topic. So the communication can be one-to-many, many-to-one, or many-to-many. And here are basically illustrations of that with publishers and subscribers and messages that are fed through a topic. Here is basically one-to-many. The publisher is sending messages and the subscribers are receiving those messages. And here we have basically two publishers that are sending messages, and we have two subscribers that are listening to the messages. Okay, now that was a kind of a high-level information of how publishing and subscribing works in ROS. Now let's jump into a little bit more how to apply this with automated driving or mobile robotics. Now here, on the right, we have a sort of example that you might apply when doing your mobile robot solution on ROS. So basically, these boxes here with the black edges, these are nodes, and then the ones with these sort of purple boxes, these are topics. And blue arrows are showing publishing, and red arrows are showing subscription. So we could have a node that is reading data from a LiDAR sensor, and it's publishing this information to a topic called /scan. And these are sort of like the topics here are topics that you commonly see on mobile robots, such as, for example, the TurtleBot that we are using on the course. Now, from the scan topic, we have a node called navigation, which is subscribing to the LiDAR point cloud from the topic /scan. And what the navigation node could be doing, maybe based on this LiDAR data, it's coming up with solutions for planning and control. So how our automated car or mobile robot should be moving in the environment. And then the navigation node is publishing odometry values, motion control messages to a /command velocity topic, which is commonly used for delivering these velocity commands. And we have a motion controller that is subscribing these motion control messages. And this motion controller could be then basically a piece of software that is then based on these commands using the motors in a suitable manner, so controlling the motors. For example, electric motors that are equipped with encoders. So the motion controller is controlling the motors, and in addition to that, it's reading the rotational speed of the motors or the wheels. And then it's publishing this information as odometry values of the robot to a topic /odom. And then this information in turn is being subscribed to by, again, our navigation node, which then uses this information as a sort of feedback loop to know how the robot is moving based on the encoder values. And then this is a ROS solution that could be then continuously running. So LiDAR data is being fed to the navigation node, which is using it for path planning, obstacle avoidance, so on. It's publishing velocity commands, how the robot's motors should be used. This is implemented by the motion controller, which is then providing feedback of how the motors are actually being used, how the robot is moving. It's providing this as a feedback to the navigation node. And all this is handled by nodes and topic communication with publishing and subscribing. So this is a very concrete example, something that you could implement with Turtlebots or some other mobile robots or autonomous cars that you use with ROS. Yeah, and as said, these topics are basically concrete examples of topics that you commonly find with ROS-based mobile robotic systems. And topics have these predefined message types that are defined when the topics are created. Now, for example, this scan topic could contain a message type, a laser scan, which is basically an array of distance data. So basically, the LiDAR range readings. The /odom could contain the odometry information, so position, orientation, velocity of the robot. And these velocity commands could be a message type twist, which are linear and angular velocities that we are giving as commands for the motion controller. So how we want to control the robot. Now, some very practical tips of when you're working with ROS-based systems, how to navigate around and sort of get an understanding of what's going on. So a very convenient command is ROS to topic list. When you type this into your terminal, you see a list of all the active topics that your ROS system is running at that moment. And if, for example, you have a Turtlebot running and you type this command, you will see something like this. You can see the topics we were previously talking about: velocity commands, odometry, scan, and so on. This is very convenient for knowing what type of data exchange is really going on in your ROS system. Another very closely connected command, ROS to topic info, with the topic name given as an argument. This basically gives you the details of a topic that is running. Typically the most interesting information being the message type that is being used in that topic. So, for example, if with the previous example of topics, we would say ROS to topic info /scan, we would get an output something like this, telling us that this message type is the sensor messages /message/laser scan. yeah, we also get the publisher count, subscription count, but commonly you're interested in this message type when you're doing your development. Yeah, and basically other types of commands that are typically convenient for development. ROS2 topic echo with a topic name provided as an argument. This basically shows the messages received to a topic in real time in your terminal. So again, going on with the previous example, if we would say ROS2 topic echo / odom, our terminal would start filling with values like this, basically continuously printing out what information is being published in this odometry topic. And yeah, this information in this case, for example, could be the position of the robot, orientation of the robot. These are quaternions. You will get to use these later on the course. Covariance of the measurement, information such as this. Very convenient for seeing what type of data is actually moving on in your topics. Another quite important command, ROS2 topic hertz, topic name as argument. It shows you the publishing frequency of a topic. So this is quite good for debugging or overall getting an idea again what's going on with your system. So for example, in a Turtlebot environment, saying ROS2 topic hertz and giving the scan topic, we could see that we are getting LiDAR readings roughly at a frequency of 5 Hz. Very good when you're working with real robots and you want to understand what type of data there is moving at what frequency. But all right, that was basically tips on working with topics. Some more tips on how to use messages. So a couple of slides back, I showed you how to print out the message type of a topic. Now, commonly, when you're doing development, you have to get to the details of the message type to understand what data is moving there, and for example, what type of information your node could be subscribing or publishing. Yeah, and there are many message formats to use, and there are a lot of basically these default standard message formats defined in ROS, and you can also create custom ones. Many times there are suitable existing standard message formats available, so always check carefully whether there would be one suiting your needs, but of course sometimes you have to create custom ones. Now, going back to the example of knowing a topic, knowing the message type and wanting to know more details, this command in your terminal, ROS2 interface show and then the topic name. Here we are providing as argument this sensor messages /message /laser scan, which was the message type used in the /scan topic. This will print out something like this, showing you exactly what information is given in that message type. For example, we can see that we have as floating point numbers, this angle min, start angle of the scan, floating point numbers angle max, end angle of the scan, and what you're typically interested in when dealing with this message type is basically this list of floating point numbers, ranges, which contains the range data of the LiDAR scan. So for each laser beam, it contains the distance that laser beam measured, something you will be using quite a lot on this course. Yeah, and as mentioned, now I've been discussing nodes and topic-based communication. There are also other ways of communication. So basically you have services, which are these short predefined functions, actions, which are these longer predefined functions, and you also have parameters, which is basically this server of global parameters that you can set or get. This can be quite convenient if you have, for example, a robot solution and you might have some variables that are then stored as parameters that you can then access. For example, maybe some dimensions related to your robot or car. Yeah, so as said, services are sort of short predefined functions, and they operate with a client and a server. So you have one node, that is the client, and they are sending a request, which is then going to the server. And then the server basically carries out the task that has been defined, and then sends a response here to the client telling that, okay, the task was executed. And now the reason why services are used for short tasks is basically that the client waits for the response. So the client sends the request, and while waiting for the reply, the client is basically frozen. And when it gets the response, then the client continues. So obviously with a structure like this, you don't want to be sending out long tasks as services, because the client node will not be doing anything meanwhile it's waiting for the task to be executed and waiting for the response from the server. So these might be some really small, simple computational tasks. Maybe something like compute a new route plan. So maybe you have received some new information and you need a new route plan to continue operating with your mobile robot. You probably can't do anything else meanwhile, so you send out this task, hey, give me a new path to follow. Quite simple calculation. Of course, depending on implementation, but still. It could be something else, such as test operation of headlights on a car, some simple hardware checks just to see that everything is operational before continuing, or something like update map information. Maybe you have a map and you found out some new obstacles or so on, and you want to add this information to an existing map. So basically, yeah, as said, services are used for these simple types of quick tasks. Now actions are a little bit more complex, with the key difference again being that these are typically used for longer tasks. And the reason is that here that the structure is similar. We have a node as the client, a node as the server, but the client is not waiting for the task to be completed. So these can be used for longer tasks. And the key difference is that while services are simple, you send a request and you wait to get the reply that it has been carried out. Here you send a request. The action server basically sends a response that it received the task. Then the client sends a request to receive updates. And then as the action server is completing the defined task, it's basically publishing feedback to the client. And the client continues its operation and it keeps receiving this feedback of how the task is progressing. And finally, once the task is completed, the server sends a response to the client sending that, hey, the action was carried out. And now the actions can be used for longer functionalities. So this could be something like, hey, follow the path to the goal point. So you could be implementing, for example, your control through an action. So this initiating a path following functionality. Or it could monitor for obstacles on the road. So this obstacle avoidance. So you would have an action server that is continuously monitoring whether there is something in front of your robot. Or it could be perform parallel parking. So this defined functionality, which still requires quite a bit of time, and also the client should remain active, doing other things such as possibly reading some sensor information, decision making, or so on. But yeah, on this course we will mainly be just using basically nodes and topic communication. These services and actions are something that are really great, but typically they require quite a well thought out architecture to implement properly and efficiently. All right, and then the third kind of extra topic of communication, as mentioned before, these parameters. So basically the parameter server is a shared place for global parameters where you can store or retrieve parameters, and these are typically something that is quite universal for your vehicle or robotics solution that multiple nodes might need access to. Maybe it might be your vehicle's dimension, or it could be some constant values. It could be PID gains, something like these simple parameters that many nodes might need access to. Okay, let's continue with ROS development. So basically the basic steps that you need to do when you're doing any development using ROS. So first thing to note is sourcing. This is something that is typically important for you to do whenever you're doing any building of your packages or launching anything ROS related. So when doing any ROS development, basically in your terminal you should source the ROS underlay. This is basically the basic ROS functionalities, and this can be sourced with this terminal command. So source /opt/ros/humble/setup.bash, and this sources the underlay. More details about this can be found in the ROS documentation, but here's a sort of like this is to give you a practical overview of what you need to be doing when working with ROS. But okay, so the underlay gives you the basic ROS functionalities. In addition to this, typically you also want to source an overlay. What this is basically your own workspace where you're working with ROS. So the workspace, a little bit more about that in the next slide, but it's the place where you have your own files, your own programs, your own packages that you use with ROS. Yeah, and that's what we call the overlay here. And to source this, you execute this command. So source then your workspace /install/local setup .bash. So you generally want to source both your underlay and your overlay from your workspace. And when doing some development, for example on this course, we are going to put these commands into your .bashrc file so that they are executed automatically when you're doing any development. Okay, so a little bit more on workspaces. These are basically on your machine, the directory that contains your ROS packages. So typically if you're following any tutorials, they basically ask you to name your workspace ROS2 _ workspace. So that's what we are going to use as an example here as well. You can name your workspace anything, but using this is quite convenient because then you will be able to follow different tutorials straight away without always having to change the name of the workspace in your commands. And yeah, all of your ROS packages, they need to be located in a workspace. And what your workspace looks like, it's basically a directory where you have different subdirectories. You have the build, install, log, and most importantly, for practical reasons, is the source or SRC. This is where you put your packages. This is where you put your codes when you're doing ROS implementations. And okay, so how to create a workspace? This is what we will be going through in the exercise as well. But here's a quick overview. First of all, you want to source the ROS underlay. Then you create the workspace folder. These are basic terminal commands that you may or may not be familiar with. If you are not familiar with these, then on this course you will hopefully learn the basics of these commands. But we are making the ROS2 underscore workspace directory, and we are making the source directory under the ROS2 workspace at the same time. Then we are changing our folder to the ROS2 workspace directory, and then we build the workspace. Now at this point there is nothing in the workspace yet, but we build it initially to establish the workspace. And for this we use the colcon build --symlink install command while being in the ROS2 workspace directory in our terminal. What this --symlink install does, it's basically very convenient. So when you're working with Python scripts, when you build with this argument, it basically saves you from the effort of having to rebuild your workspace every single time when you're changing Python scripts. So as we're working with Python on this course, you generally want to always include this flag here when building your workspace. Yeah, and as already presented, you can then source as an overlay the workspace with the source ROS2 workspace /install /local setup.bash. But yeah, as already said earlier on in this video, think of packages as project folders for ROS. They are single units of ROS software which can be installed or shared. And generally, your package looks something like this. This is something that, again, you put in the source folder, but you have your package as a folder, and it contains package.xml, which contains meta information about the package. You have this resource /mypackage, setup.cfg, setup.py, and then you have this another folder called mypackage within your package, which then actually there you have your Python files or your code files directly under that subfolder. And yeah, here you can basically see the explanations for these different files. Yeah, so typically this meta information is generally relevant, then setup.cfg, setup.py, and then of course the directory with your package name where you insert the source codes. Okay, so how to actually create a package then? In ROS2, packages are created with this command. So ROS2 pkg create. And below here's a basically sort of let's say quite general minimalistic example of how you would go about creating a basic package in Python. So basically to the ROS2 pkg create command, as an argument, you have to give the package name, so the name of the package that you want to create, and then there's multiple flags that you can or oftentimes have to provide. So basically, you have to provide the build type. Now most of the time, you want to use this amend_cmake as a flag. There's an alternative you can provide, this amend_python. This amend_python is basically a build type that you use for pure Python packages. But this amend_cmake is basically a more general format, and typically you want to use that because, well, it allows quite a wider range of ROS features when you're using that to build your package. Also, as a flag, you can give the dependencies that your package depends on. Here we are providing rclpy, which is basically the basic dependency that contains the Python libraries of ROS. So when you're using Python, you typically want to list this as a dependency, since it provides you the basic node and communication functionalities of ROS. Oftentimes you also want to provide this std underscore messages. So this basically is the standard message formats that most of the time you want to use when you're working with ROS. Yeah, so what the dependencies are, these are basically the libraries and tools that your package relies on to operate. And the build type, this is typically ament underscore CMake or ament underscore Python. And most of the time you want to choose ament underscore CMake, but for pure Python implementations, you can also use this ament underscore Python. Now, building a package, previously we were talking about building your workspace, but building a package is basically the same thing with a little bit more details. So basically, when you're creating packages, you must build them before using them. And if you update your packages, you have to build them again. Except if you're using Python and you are building with this symlink install flag, then you don't have to always rebuild when you're updating your Python scripts. But how to build packages? Basically, you have to change your folder in the terminal into your workspace, main workspace directory, and there you can either build a specific package with this command. So this is what we used to also build the workspace, with the addition that we had this packages select argument where you insert the name of your package. So this builds only the package. This builds only a specific package that you want to build. And then if you want to build all packages, this is the same as building your workspace. So doing this colcom build symlink install for convenience on Python. Yeah, and again, you should resource your workspace after building packages. Now, how to import an existing package? This is something that you have to do in practice quite a lot, because as already discussed, ROS is a really good platform or middleware for the reason that there are a lot of open source resources available. And how this works in practice is basically you can find packages online and then you can download those packages. Or well, that's one common way to use the different available ROS software. Yeah, but for downloading, importing an existing package, generally you want to go to your workspace source folder, then you clone the package, generally from GitHub. This is where you can basically find majority of let's say open source ROS packages. Then you need to install dependencies for that package, or well, it is an optional check to make sure that you have all the dependencies that you need for the package. And then you build the workspace or just a package, as was described on the previous slide. So in terminal commands, you basically first navigate yourself into your workspace in the source folder. Then if you are downloading your package from GitHub, you can clone it with this git clone command. With this command, you basically get the basic ROS tutorials provided by ROS that we will be showing a bit of examples later on. Then you need to switch back to your workspace source folder. You can install the dependencies with this command. Basically, it looks into your source folder and identifies the missing dependencies, and then again building your workspace or building all packages with this command. And this is a general guidelines for when you find an existing package in GitHub and you want to download it into your workspace to use it. So let's jump a little bit deeper, looking into ROS program files. So now we're getting the very practical topics of how you create your programs, how you code the functionalities that you want in your robot or automated vehicle. So we are talking about implementing nodes, which, as said, these are the sort of like a basic implementation of functionalities in ROS. And how you implement nodes is by basically creating source code within your package. So again, your path could look something like your workspace, source folder, the name of your package, and under this directory you insert the code for your nodes. And when you're implementing nodes, typically what you are is basically implementing publishers and subscribers. So you are implementing units of functionalities that are performing some processing and then subscribing to some topics or publishing to some topics. And basically the following slides will give a concrete example how to create with Python a subscriber and a publisher in ROS. And of course, to follow along, basically you should start by creating a package. Here you can build a suitable package with these commands. So we are naming our package py_pub_sub. We are basically following, in these slides, we are following the basic ROS2 tutorials, which are also a great source for looking more deeper into these examples. But okay, here we now have a basically minimal example of a publisher that is from the ROS2 basic documentation. Now, if you want to follow along with this example, you can basically create a file named publisher_member_function.py, place it here in your workspace under the py pub_sub folder, and insert these contents into this file. This script can, instead of copying the contents, you can also download this script with this command, which downloads the Python script file from the ROS tutorials. But okay, let's look a little bit what goes into implementing a minimal ROS node that publishes information at certain time periods. So first of all, we are importing RCL_py. This contains basically the basic ROS Python functionality. So this is something that you are pretty much always importing. Then we are importing the node functionalities from this RCL_py, and we are also importing this string message from the ROS standard messages. So standard messages is a dependency for our this package implementation. And then these node functionalities are created as a class in Python. So if your memories of Python are a little bit rusty, I recommend checking up on how you actually create objects or classes in Python. But what we are doing here is basically we are creating this object minimal publisher that inherits from the class node, which is something that we imported. And in the initialization, we are basically naming our publisher minimal publisher, and here we create the actual publishing functionality. So it's self.publisher _ equal to self. We are using the create publisher that is coming from the node. Create publisher method that is coming from the node class. And as an input to this method, we are providing the message type, so string that we imported here. We are giving the name of the topic, here just simply named topic, which defines the topic that we are publishing to. And here we are basically defining the queue length for this topic. So basically, if how many messages there are in the queue if someone is not subscribing them as fast as we are publishing. Yeah, here in the initialization, these other lines are just basically about creating a timer that every half a second calls this timer callback, which is this function that then actually performs the publishing with that created publisher, self.publisher. So what we do here, we are publishing, so we need to publish a message, right? So what we are doing is we are defining that message. This way, we are basically saying that this message variable, it's basically an empty message of this string type. And then in this data field, message.data, we are inserting the actual information. So in this case, simply just a string of hello world with an incrementing number as the timer is incrementing. And then here we are doing the actual publishing. So remember this method is called at specific time intervals. So here we are using the publisher to publish this message. So the string of hello world with the incrementing number. Yeah, and here we are just simply creating a main loop. We are initializing the ROS Python functionalities. We create an object of the minimal publisher class, and here we are then spinning the object. So in a way starting it, and here it's just basically if the node is closed down. Here are commands to destroy the node and shut down the ROS Python functionalities. But okay, so now same thing for the subscriber. So minimal example from the ROS documentation with a similar name, subscriber _member _function.py, and this is created in the same folder. So py pubsub, py pubsub. Yeah. And again, the contents are presented on the right, but you can also get this script directly by putting this in your terminal, which downloads the file from the ROS tutorials. Yeah, but so now we are making a publisher, a subscriber that subscribes to the information that is publishing to the node that we created in the past slide. And if we look at the imports, we can see that we are importing the same things. And again, we are creating a class that inherits node. This time it's minimal subscriber. So last time we were creating a publisher, so we named it minimal publisher. But these are, of course, just the name of the class. So you can name your node anything you want. Yeah, or the name of the node is actually specifically here in minimal _ subscriber. This is just the name of the class that implements the node. So the node name is here, and node names should be unique. So you cannot have multiple node implementations with the same name. But this is again very similar to the publisher. So in the initialization, we are creating the actual subscriber or the subscription with this create subscription method. As an input, we are giving again the message type string that remember we imported here. We are giving the name of the topic that we are listening to, that we are subscribing to, and we are defining this method, this listener callback. This is an important part. This basically defines what is done each time that the subscriber receives a new message from the topic. And here we are defining the queue size again. And and then as said, this listener callback is sort of the main functionality here. And this method is then implemented here as an input. It takes the message, so it takes the information that is coming from the topic. And here it's just a dummy implementation of what the subscriber is doing. It's basically just logging the message that it heard into a ROS log. Now, if we were not making a minimal subscriber, if we were making some actional functionality, here you would basically include the processing of what you would be doing with that data. Maybe you would be receiving a message of LiDAR data, and here you would implement some processing which maybe extracts objects from that data, or maybe it makes some mapping or something like this. But here it's just a dummy implementation, so we are simply logging the information that we heard. And yeah, this main functionality here, again, just to sort of like make this executable, so that when this script is executed, it basically initializes this ROS Python functionalities, creates this minimal subscriber object with the class, and then launches this subscriber. And again, these are just here to basically nicely handle destroying of the node when it's shut down. But okay, now a little bit about dependencies and entry points, which are basically the things that you need to take care of to make sure that it's properly defined what your package depends on, and also to enable the actual execution of your node. So we showed the contents of those nodes, but we need to define that, okay, these are actually something that we are able to execute on our ROS system. So when it comes to the dependencies, as said, these created example nodes, they depend on libraries RCLPY and std_messages. And these are basically the things that are imported in the Python code. And now the things that now need to be configured in the package to basically explicitly state that these are the dependencies. In the package.xml file that is included in the main folder of the package, you need to add these lines that basically define these dependencies. Yeah, so this is something that you always need to do when you're creating packages, creating some nodes in them that depend on different ROS functionalities or libraries. You need to insert these dependencies, or the dependencies that your node depends on. But okay, that was the first thing, the dependencies. Then to the entry points, or well, how to make these executable so that you can actually run them. This is something that you need to insert into setup.py. So there you need to basically define these entry points. So you're defining, here we are basically giving, you can see that we have the package name. Under this console scripts, we are defining which nodes we can execute from the console. You can see here we are putting the package name. Here we are putting the name of the file without the .py suffix. And then like main, we are defining the function. That's the executable. And we are naming this talker. So talker equals this. Talker is our publisher, and then listener is basically with the same syntax, the subscriber. And yeah, this talker and listener are the sort of names that we are defining for the execution. And then after those configurations and after building the package instructions provided in previous slides, the created nodes can be executed with these commands. And as said, that we use the talker and listener names here, because those are what we defined as the entry points. So we can say ROS2 run, name of the package, and then name of the executable. Yeah, and as said, the publisher we created, it's basically a dummy publisher, just at every half second publishes this string message with this incrementing number. So if we run the publisher, the talker, and then we run the listener, the subscriber, we will see something like this. So in the terminal, the publisher is basically logging what it's publishing, and then the subscriber is logging the messages that it's receiving from the publisher. So this is a very simple, minimal publisher-subscriber communication. But okay, there we showed how to basically execute these nodes as standalone executables from the terminal. Now, of course, if you are dealing with sort of larger packages, more complex systems, you don't want to be in your terminal running every single node separately. Things get messy really fast. So an important concept here are launch files when it comes to ROS. So what these allow is basically, instead of one by one running your nodes, you can make a launch file which basically then, with a single launch, can perform multiple actions, such as running multiple nodes with different parameters and so on. So when you start getting into more complex ROS projects, you start getting more and more familiar with ROS launch files. Launch files in ROS, they can be provided in several different formats. They can be XML, YAML, or Python files, each having their own distinct syntax, but the basic contents are pretty much the same. So you are within the launch file, you are specifying which nodes are launched with which parameters and so on. Yeah, with additional information that can be linked configuration files, etc. And launch files should be placed within your package in a separate folder named launch. And here on the right you can see very minimal example of a launch file in this XML syntax, which would basically launch those two nodes that in the previous example we run one by one from the terminal. So if you would create a launch file for launching these, it would look like this. So you are defining this launch within these brackets. This basically starts the launch, and here we are ending the launch, and then we are defining the nodes here. So we are defining the package, then we are defining basically the entry points that we configured previously. So we have the talker name for the subscriber. We are using name for the node that is unique, and we are also providing an output, so where the logs are being displayed. Here we set it as screen, which means that the logs are then printed in your terminal. And then same thing for the subscriber in this example. But okay, as mentioned previously, most of the time you are working with nodes and topic-based communication, but there are these other ways of communication as well: services, actions, parameters. Let's take a quick look at how to implement a service as well. We won't go into as much detail as with that creating a publisher and subscriber, but let's take a look at this. Again, following an example from the documentation of ROS2. So to follow along, you should first create a new package for the service with this command. We are basically calling our package py_srv CLI. And now we are adding the dependencies here, rclpy example interfaces. These previously we basically inserted the dependencies into the setup files, but now we are already creating them as we are creating the package. So we don't have to manually insert them into that package.xml. So you previously we inserted the dependencies into the package.xml file, not the setup files. With this, by already providing them when creating the package, you don't have to manually insert them there. And this example interfaces, it's basically a package that for this example contains this .srv, this service file, which defines the service call that we are using here. So when you're calling a service, you always need to define the format of the call that you are using. This basically defines the input and output of the service. So basically, in this case, our input are these two integers, a and b, and then the output of the service is this integer sum. And this is now a service type that has been defined in this example interfaces dependency. But okay, let's look at the code. This script is called service underscore member underscore function.py, and again we are first importing needed dependencies. Here we are importing from the example interfaces this add to ints service interface, which is basically what I showed here already. And as you're already familiar with, we are importing the Python ROS functionalities and also this node class. And similar to creating the node for publishing and subscribing, we are defining this class minimal service, and it's inheriting this node class. Again, similarly in the initialization, we are giving a name for the node, and we are then actually creating the service. Very similar to what we were doing with publisher and subscriber. We are using this inherited method create service. We are defining the service interface, defining the inputs and outputs. We are giving a name for the service, and we are defining the callback function. So the callback being what happens when someone calls this service. And then basically the definition of this callback is here. As an input, we are getting request and response. And basically within the request, we are getting the information defined by the interface. So in this case, the integers a and b. And what this service does is it adds two integers together. Just a dummy service to show the operation. So what we are doing, we are saying response.sum, the sum being defined here as what we are outputting, and this equals to request.a plus request.b. Since we are just summing them together and storing the sum here. And here we are just logging information, and from the callback we are returning this response. So as explained previously, service is something that you feed data into in your request, and as a response you get some information. So the request information is in this example summed together, and the response that we are returning is that sum. So just very minimal dummy example. The main for making this an executable, again, very simple. We basically initialize the ROS Python functionalities. We then create an object of this minimal service class. Then we launch that service, or we start the service, and then if the service is closed, here we define that we are shutting down the Python ROS functionalities. And then basically for the node, because now previously we defined the server, which then actually carries out the service, and then now we define the client node. So the client is the one who calls the service. Here we are naming the file service underscore member underscore function.py. Here within our py underscore srv CLI package. Again, the actual code is provided here. Yeah, as a sort of like tip for testing that is often convenient anyway ROS development, instead of creating your specific client node, you can also use this very simple command line interface for calling a service. So kind of just basically a one-liner for creating a very simple client node. So this ROS2 service call, and then here you basically insert the response message in the format that is required. This creates a basic service call which then outputs the response to the terminal. Yeah, as for the code, again, quite straightforward. The main difference here that we are importing this sys, which is basically because this node is when this node is used, when you run the node, you provide the two integers as the input as arguments to the actual command line running of this client node. But okay, we can see again we have quite simple implementation following the basic structure that we've shown previously. Won't go too deep into this, but we can see that we are basically creating the client here. We are defining the interface, also defining this service name, or service topic that is basically that the service which this client is specifically calling. And here we are basically creating the request variable. And in order to send a request, we simply populate the data fields of that request variable with the provided data. And then we use this command to basically call the service with this request. Yeah, there's a bit more going on here in the actual main executable of the implementation. I won't get too much into detail here. You can always go into ROS Wiki and check out the details. For many tasks, this simple command line client interface is quite good for different testing, debugging, and so on. But of course, for a proper implementation, you should implement your own client node. And for details, you should check out the ROS Wiki. But okay, then service configurations. So how to actually then make these files executable. It's the same way as we were previously doing with the nodes and the topic-based communication. So in the setup.py, you basically define the executables in the same manner. And then running the service, running the service server. This is how you run the service server. So we named the server as the service. We ROS2 run, again the package name, and then the node name, the name of the entry point for that node. And here is how you would run that Python implementation of the client. And as said, the actual executable is a bit, the implementation is a bit more complicated since it's taking these variables as an input. Yeah, but that's how you implement a basic service. Now, all the previous examples were basically using predefined message type, predefined interfaces, and so on. So let's talk a little bit about when you need those custom solutions, how you would do that. Okay, so ROS comes with a very good set of existing standard message types and interfaces, but of course oftentimes you run into a situation that you have to create your own custom ones based on whatever it is that you're exactly doing. And now all the previous tutorials, previous content shown has been using the existing standard messages and service requests and responses. So let's take a look at how you would actually go about creating your own custom ones. And the way to do this is basically that you have to define your own custom messages and service interfaces within a package. So when you're creating a package or working on a package, you can define these within the package, and also from other packages you can then import defined custom message formats and service interfaces. And now, if we would want to create our custom messages and service interfaces, after creating that package, within the package main folder, we would create a directory named message and a directory named SRV. So MSG and SRV, separate directories. And within these directories, in the message directory, we would basically define our custom messages. So just some examples. If we wanted a simple message named num, that is basically just a single integer, we would define a num.msg file and write this content in it. Same thing for if we wanted a sphere.msg. This is an example of basically combining existing standard messages with some custom information. So in this message, we would basically insert a geometry message from the standard messages. So we would have geometry messages /point, and the name of the data field would be center. And here we would have a floating point number radius. So we are taking a standard message, this geometry messages point, and adding another field of data into it, creating a custom message sphere.msg. And these would go into the MSG folder. Now into the SRV folder, if we wanted a custom service request /response, we would do it the same way. So create the file with the name of the message that we want to have, and then defining in the file basically the request and the response as well. With this example basically being the same as previously, the add two integers, but instead we've added a third integer in here. So we have three integers as the request, and as the response we have one integer called the sum. But okay, so you've created those files, you've created those definitions for your custom messages and service interfaces. What then? Well, then you need to do some configurations on your package so that it's actually capable of using those definitions in those .msg and .srv files that you created. And the way to do it is illustrated on this slide as a direct example to those example files that we were using on the previous slide. I won't go too much into detail here, but basically for this example, to make it work, you would need to append these contents into your cmakelists.txt file. This is a file that you can find on the source folder of your package. And this information that you're inserting, basically you're inserting the knowledge that this geometry messages is defined, this standard message format was used as part of the sphere message. And we are also defining that we need to use this ROS generator package. This is basically then something that generates the definitions based on your files, very much ROS internal stuff. But okay, in addition, we also need to define that what we are generating interfaces for, and here we are basically putting the paths to the files we created. So the the files that contain the definitions for this message type, and also the file that contains the definition for this service interface type, and also here putting the dependency that we have on that geometry underscore messages. And we also need to append a little bit of information to package.xml. Here we are also, this is again a file that you will find within your project. And here we are also defining that the dependency on this geometry underscore messages, and then we are including some additional information regarding this ROS IDL generator. Let's not go into detail there. Again, quite internal ROS things, but yeah, these are basically the information that you need to include in order to be able to create these custom messages based on the definitions within the created files. And then when creating nodes in another package and so on, whatever nodes, provided that you've included this package as a dependency, we can then use these messages and service interfaces in our Python code such as this. So basically, if we wanted to import the, let's say the num message type, we would basically say from package, referring to this package where the messages are defined, .msg import num. And this is how you can create your own custom messages and service interfaces for use in your own Python nodes. Another topic to talk about customization, oftentimes when dealing with these ROS systems, you are dealing with different coordinate systems. The sort of easy example here being that maybe you have a robot, and then maybe you have a camera on that robot. And when it comes to the robot coordinate system, that's typically defined somewhere. Maybe it's at the center of the robot. Maybe if you have a car, then the main coordinate system is typically placed on the center of the rear axle. But then you have also sensors on your car or on your robot that are processing data. And these sensors have their own coordinate system. And a very common thing to do or define in ROS are these transforms. So how you transform data from one coordinate system to another. For example, let's say you have a stereo camera and you are processing some information from there, getting, let's say, coordinates of obstacles. How do you transform that information to your robot frame to know how to use that in your navigation and path planning and so on. And in ROS, there are two main kinds of transforms. You have static and dynamic transforms. And the one that I've just been describing to you is a static transform, because if you have the camera rigidly mounted on your robot, the transform between the robot coordinate system and the camera coordinate system remains the same. But you also have dynamic transforms, which means that the transform is continuously changing. This could be, for example, you have a coordinate frame for your map or your world coordinate frame, and you have your robot coordinate frame. And if you want to transform information between these two coordinate systems, you need a dynamic transformation, since your robot is moving in the world, in the map, and therefore this transform is continuously changing. And how you implement transforms in ROS is with this TF2 package. And now a simple example of how to set up a static transform, where we're not going to discuss the dynamic transforms here. Just to giving a simple example on these static transforms, because these are something that you oftentimes need to define when doing even some basic work on robots. How you do this is you basically define a transform publisher in your launch file. So in this case, if we are defining a transform between the robot frame and the camera frame, the robot frame here being base link and the camera frame here being the camera link, here, and then let's say that our camera is 1x coordinate from the base link. So this could be maybe in meters. Let's say our in the x direction of the robot frame, our camera is 1 meter in x direction. And then in y and z directions, there is no offset. And for the sake of example, I mean, let's say that there is no rotation involved. So roll, pitch, yaw, all those angles are 0. So it's just 1 meter offset for the camera coordinate system. How we would define this is if we have an XML-based launch file, we were talking about this previously as well, you would create this node, which is from this TF2 ROS package, with using this entry point or executable static transform publisher. You can give it your own custom name, defining that the output is going to be logged to your terminal window, and giving as an argument then this translation and rotation information. So X, Y, Z, roll, pitch, yaw. And then the transform being from the base link to the camera link. So this is a simple way to define transformations in ROS. And then when you actually want to use that information, let's say you want to you need to transform some information from the base link to the camera link. Here is a sort of like very minimal, simple example. So you need to import from this TF2 ROS. You need to import this transform listener. This buffer here is just used to implement the buffer for the transform. But then within the node class, really simple implementation. Not going into full details, just kind of showing the main points here. You create the buffer and you create the transform listener in your initialization, and then to actually get the transform, you basically call this TF buffer lookup transform, defining from which coordinate system to which coordinate system you want to have the transform. And also defining the time here and the timeout in case your request doesn't get a response. But really simple. This is how you initialize. Here's how you get the transform in your own node implementation. And last but not least, let's discuss a couple of really convenient tools for development that ROS offers. When you're working with ROS, you probably want to very quickly get familiar with these tools because they will make your development, debugging, and so on quite a lot easier. So first of all, RVis, this is something that we use also quite a lot on this course. It's your go-to visualization tool with ROS. So you can use it to visualize sensor data, different coordinate systems, the transformations, map information, trajectories, all kinds of things. So it's basically your main solution for visualizing all the information that your autonomous car or robot is processing. And now to run RVis, you basically run it with this ROS2, run RVis2, which opens a window such as this for you. Now, of course, when it comes to actually configuring all the information that you're visualizing, that requires custom configurations. There are quite a lot already existing good solutions to use out of the box, but it typically requires a bit of configuration. But anyway, RVis, really convenient for visualizing all types of different data from a mobile robot or autonomous car. Now, ROS bags, these are your go-to tool for data recording in ROS. So if you have a ROS system running, you can simply start recording a bag, which means that all all the information that you choose to record is stored in the bag. And later on, you can play that bag, and then playing that bag on a ROS system basically sort of creates, it repeats all the information that was recorded. So you are effectively creating a sort of like ROS virtual replica of everything that was going on in ROS during time of recording. So if you want to record all topics, you do it like this, ROS2 bag record -A for all. And to play the bag, ROS2 bag play, and then name of the bag file. And let's say I had a robot and I was running a LiDAR, and I recorded that LiDAR information. Whenever I play the bag, it will play out all the messages in the topics that were delivered during time of recording exactly the same way as they were on the time of recording. So I can go out, operate my robot, record the sensor data, go back to the office, play the bag file, and get the exact same exact replica of all the data that was in ROS, the exact same way as it was back when I was recording it. This is very good naturally for a lot of different development purposes. Last but not least, a really convenient tool, RQT Graph. What this tool does, it basically provides you a way to very conveniently visualize all the nodes, all the topics, and their connections. This is really convenient when you want to get a sort of overall picture of what's going on in your ROS system. So if you have ROS running, a bunch of nodes, bunch of topics there, running in your terminal, ROS2 run, RQT Graph, it launches a view like this, where you can basically see all the nodes as ellipses, and then all the topics. So the nodes are these ellipses, and all the topics are these rectangular boxes. Yeah, and then the arrows are indicating data flow, so basically publishing and subscribing relationships. So it's very convenient. You can see how all the information is flowing. You can see that, okay, we have the teleop turtle node. It's publishing velocity commands through this topic. We have turtle sim here that is then subscribing to that information and then publishing information to a topic, this turtle1 pose, and so on. So anyway, RQT, when you have a ROS system and you want to get the sort of big picture, who gets what information, use RQT Graph.